where I left off last time talking about optical recording was the idea that it's called optical recording because you read it and sometimes write it optically, that is using light, and the best light source for this sort of activity is a laser, simply because it produces this one giant wave that you really can manipulate carefully and with precision using optics. Ordinary light, you just can't work with it that way. So, like any wave, you can only focus light to a certain narrowness. You can't focus it to a mathematical point in space, even though the equations of what are called geometric optics, optics forgetting the wave nature of light, just going ahead, will predict that you can make light, you can narrow light down, you can focus it to a spot, to a single point in space, and then it spreads out after that. You can't, because of the wave nature, it goes to what's called a beam waste, that's the conventional name for it, which is related to the wavelength of light. It depends on characteristics of the beam entering the lens and the character of the lens as well. But it's pretty small, but not infinitely small, and that's the point. And therefore, you can't illuminate features on the surface, on the information surface of a compact disk that are smaller than about the wavelength of light. And that has limited how much information they could put on, first on a CD, then on a DVD, and then on a Blu-ray disc. As the lasers that were available became shorter in wavelength, they went from infrared for CD to red for DVD to finally to blue for Blu-ray, they can write smaller features. And yeah, consequently, they can put more information on the Blu-rays, which is... Any questions about this before I leave it? I want to name this behavior just because it's going to show up on the next problem set, which will appear over the weekend. It's called diffraction. That in effect, if you try to pin down a wave to a small region in space, you trim away its side features. Those features were useful in keeping the beam small. The nature of the beam's propagation through space, but any laser beam, involves interference effects. That namely, in the beam, the interference effect is all constructive, and outside the beam, where it's dark, it's all destructive interference. And if you chop off parts of the wave on the sides, you're removing parts that were important to the interference process of keeping the wave local and small. You chop those off, and suddenly you start getting... You don't get constructive interference outside what used to be the beam. The beam gets bigger as a result. This shows up in places you'd never expect. For example, in telescopes. One of the reasons why telescopes have larger and larger mirrors is because, and they're now all mirror-based rather than lens-based, because there's no color problem with mirrors. The reason for the giant mirrors is that you're taking a wave that's been traveling across space for eons. It's a big, vast, broad wave, and you're chopping it off as it goes into the telescope. And that act of chopping off the edges limits its ability to focus. And the interference effects are all there in the telescope. And the bigger the mirror is, the less it chops off the wave, and the tighter they can focus it. And so the features that you can see in the telescope become finer as the telescope's mirror gets larger. And that turns out it really matters. They also want to collect a lot of light, but being able to avoid the interference problems is sometimes even more important. So in some cases, they synthesize a giant telescope out of many separate pieces of telescope. They're not even necessarily so concerned about collecting lots of light. They want lots of resolution. They need a piece of telescope here, a piece of telescope here, and a piece of telescope here. Obviously, it misses the light that didn't hit those telescopes, but they're able to work with the interference pieces to create a tighter focus. All right? Okay, I get on my harangues. I can't stop. One last thing. Sometimes you've seen pictures of images taken through telescopes, and all the stars, particularly the bright ones, have starburst shapes around them. They have for example, a cross, or maybe 6 light streams coming out of it. Hopefully this is vaguely familiar. What those are actually are interference patterns caused by structures in the entry to the telescope. Telescopes often have, since they're mirror-based, the light is coming from a star, it goes into the telescope, off the mirror, and then back out to the place that collects the light, where the image forms, where they collect light. And that place where they collect the light is supported by something. It's not hovering in space. And the supports themselves, which there might be 4 of them, those create an interference pattern on every star because they block part of the wave. And you get the star-shaped images of the stars. In fact, the imaging device itself blocks part of the wave. And so all this adds imperfections to the images that you can see in the final photographs. All right, with that I'll leave optical recording. Last thing I want to talk about in this context of information communication stuff is, oh gosh, I'll leave this alone. Carrying light long distances. And so this is the story of fiber optics. And the issue with fiber optics is in the old days of broadcasting information by radio, you basically used all the channels to convey information one at a time until they were gone, until all the channels were full of activity and nobody else could broadcast information. One solution to this was to broadcast inside a cable. And the original cables were cables that were electronic in nature. They were typically coaxial cables, which, if you've got cable television, in all likelihood, showing up in your house is a cable, a metal pipe with another metal wire running through the middle of it, what's known as a coaxial cable. The details of this environment don't matter, but there's basically an electromagnetic world inside that pipe. It's assisted by that central wire, but there are electromagnetic waves traveling in the gap between the central wire and the outside cylinder. And suddenly the whole spectrum of frequencies, all the radio waves from as low frequencies as you like to about a billion cycles per second, sort of into the microwaves, can live inside this cable. They are traveling in the gap between that wire and the outside. The wire and the outside, what's called the ground, is both those metal portions are involved in the wave, but the wave is primarily traveling in the gap. And because it's inside the cable, you can use it, and your neighbor can use it, and you don't interfere with each other. So once cable television started showing up and cable communication started showing up, you suddenly had a lot more information could travel from one place to another because you weren't all stepping on each other's toes by using the same electromagnetic waves, and therefore your neighbor's receiver would receive waves destined for your receiver and vice versa in the open broadcasting world. Okay, well, cable has been around for a while, and now it's gradually being replaced by another electromagnetic conduit, and this is fiber optics. And so now, instead of sending an electromagnetic wave in the radio and moderate microwave region, you can send a wave as light. Whether it's visible or not doesn't matter. It's near the visible, give or take. And those fiber optics are again an electromagnetic conduit that carries the information, and through one fiber is separate from through another fiber. They don't interact with each other, so you can keep using the frequencies over and over again for basically as many of these fibers as you want to have. So the question is, how does the fiber work? The fiber, it's basically a transparent tube. The light is going through a material the whole way, so it better be really transparent. So the glasses used inside, used to make fiber optics, they're either plastic. They're plastics for fun and games, but for actual communication, they're serious glasses that are just the most pristine, transparent glasses they can make. They're amazing glasses, really. And the trick then is to keep the light in the glass. And ordinary mirrors aren't suitable for this. Ordinary mirrors that you're used to, like the aluminized layer on the back of a bathroom mirror, that layer reflects about 95% of the light that hits it, give or take. It's not perfect. And one bounce off of it is good, second bounce a little dimmer, third bounce a little dimmer still, and so on, until finally there's not much light left. And you may have occasionally stepped into a bathroom where there's a mirror on one wall and a mirror on the opposite wall, and you can stand in the middle of the two and sort of see yourself over and over again. Is this ever familiar to anybody? It gets dimmer and dimmer as you go off into the distance. I mean, usually they're not lined up quite well enough, so your image, there's your image, and your image, and it sort of drifts off into the off at some cockeyed angle. But even so, you can tell it's getting dimmer. So if you want to trap light in a piece of glass, a long, thin piece of glass, you want the reflections off the walls to be perfect, not pretty good. You need it to be perfect. And they are. And the trick for this is an effect known as total internal reflection. If you think back to this, when I first talked about refraction and refraction, when light encounters a surface and slows down, it bends toward the perpendicular. Remember that idea? And when it leaves a material that travels slowly into a material that travels fast, it bends away from the perpendicular, right? That bending away from the perpendicular is interesting because if you can get the light into the glass, so it's inside the glass traveling at a very shallow angle to the exit surface, then when it bends away from the perpendicular and trying to leave the glass, it can bend beyond 90 degrees from the perpendicular. It can bend so hard that it doesn't make it out at all. So getting the light into the glass is a story we'll have to deal with. And I got to change the batteries in that poor guy. Is this guy? That guy's right. Good. So the light, how you get the light in the glass, we'll work on in a second. You can't do this with just a window from one side of the window to the other, because you want to get the light so it's traveling not straight out the exit, or even at a pretty sharp angle to the exit. You want it coming at a pretty shallow angle to the exit. Here's the exit. This is air. This is glass. If it comes in here at a pretty shallow angle, it bends so hard away from the perpendicular, which is this direction, it doesn't make it out at all. Zero exit. And this is an effect where I've seen it the most is if you look into an aquarium and you look at the sides of the aquarium. So here are the fish swimming by. Here's the aquarium, and you look at the sides, like where my hand is, these two. In certain circumstances, they look perfectly mirrored. And I hope you've noticed that one too. You hold your hand outside the aquarium, you can't see your hand. You see a perfect reflection back into the aquarium. And what that is light that's in the aquarium going at a shallow angle, tries to exit out the glass to head off into this land over here. It doesn't make it. It bends and comes back at you. So you're looking at light that was trying to escape and didn't. So one of the demonstrations they've got here in the collection is this one. If I send laser beams just straight down, of course it goes pretty much straight down, not a problem. But if I send it at a shallow angle, I got to get this. Oh, there it is. You can see it. It's trapped in the glass, in the plastic. It's going around, swirling around. It's bouncing back and forth across the sides. It's hitting them at such shallow angles. It's trying to get out. It can't. Trying to get out. It can't. Back, and it works its way all the way around in a loop. And you can see it down here, having made a full loop around that plastic pipe. I haven't used this demonstration before, but it's a good one. Okay? So the light's trapped in there, unable to escape, because of this total internal reflection effect. Yeah? Why is it bent? It's because the pipe itself is arcing around. If I had a flat sheet here and I shown it in, they've got a nick here to make it possible. They probably polished it to make it so you can get the light in properly. Because it is tricky to get the light into the glass so that it's traveling at a shallow angle. Once it's in there, it's trapped between the inner and outer surface of the pipe. And it's just trying to get out, but as it's going at an angle, and it just follows around the pipe. If it were a sheet, it would go straight. And the only reason you actually see it en route is because there's dirt on the surfaces that is allowing a little bit of it to escape. When the light hits the surface, if it were totally pure, pristine, and perfectly flat, it would reflect 100%, you wouldn't see any. But because there's gunk on it, the slightest bit of gunk will allow it to escape. Another example where you've probably seen this is if you have a cylindrical glass of water. You have the same problem. You look at it in certain ways, it looks mirrored. And what you're seeing again is light trying to exit the glass at a very shallow angle, bending beyond 90 degrees and just reflecting perfectly. And you can ruin that perfect reflection with your fingerprints. When you grab the glass, you see your fingerprints. I hope this is familiar to you. I mean, physicists on one hand are remarkably unable to notice everyday stuff like, oh, there's a tree there that I've been traveling here 30 years. I've never seen that tree. Okay, so that, physicists can do that kind of stuff. All right, yeah, and there's the famous joke, what do you call a physicist who is looking at someone else's shoes, plural? An extrovert. All right, anyhow, so physicists are able to miss like really obvious stuff, but they're also not completely, so if I've noticed my fingerprints there, I mean, that may be something else, like we notice weird stuff, like, your fingerprints show up on the glass. I hope you guys have noticed your fingerprints on water glasses. When you look at the right direction, it's a mirrored surface. Oh, wow, it's mirrored. Oh, I touched it, I see my fingerprints, okay? I've now beaten that to death. Look for your fingerprints on water glasses. What you're doing when you do that is you're spoiling total internal reflection because the wave hits the surface at this shallow angle and tries to leave. It actually does there is an electric and magnetic field a little bit outside the glass, trying to become a wave that will travel. It figures out, nope, we're at too shallow an angle, we have to do perfect reflection. But you can frustrate the total internal reflection by giving it another surface to enter, like your finger. And your finger will allow it to escape. Yeah? If it's at a shallow angle, why does the bend exceed 90 degrees? The angle I have in mind here is look at this ray right here. This ray will bend away from the perpendicular, and it was arriving maybe at a 30 or 5 degree angle from horizontal, and it bends to like 80 degrees from horizontal. So the shallow angle I have in mind is the angle between the light and the actual surface. So this angle then is somewhere in the vicinity of 50 degrees. By the time you get to this ray, the angle there is down below 40 degrees, 30 degrees maybe. And so that's the shallow angle I have in mind. That it's just trying to slip out at a almost parallel surface. And when it does that, to satisfy the laws of refraction, it has to bend away from the perpendicular so hard that it goes beyond 90 degrees. The naming of things, what are the conventions? If this is the perpendicular here, along here, this ray was traveling at maybe 30 degrees away from perpendicular. The ray leaving is traveling more like 85 degrees away from perpendicular. And the next ray up here was traveling maybe 45 degrees from perpendicular, and it would have to travel at 130 degrees from perpendicular on its escape. And it doesn't manage to escape at all. It bounces off. Is this followable? The picture hopefully just sort of illustrates it. You can get it from gut feel from your camera. Why does it work with a laser pointer and not with a flashlight? It should work with a flashlight too. It's just the light is so concentrated, intense with the laser pointer. You can see it swirling around. If I use a flashlight, this will be relatively concentrated. Let's see. There's a little action going on here. Do you guys see it at all? It's trying. It's sort of, and actually there's a lot of light coming down here. How do you think the light managed to get down here? It was diffuse, it was working its way around. If I just shine it straight in, we don't get a uniform illumination. If I go to cockeyed, it is coming around here. Okay? And lots of toys that make use of this effect. Actually, I mean, here's one. I can take the laser pointer. There are a whole bundle of fibers going through here and coming out here. So there they are. Right, I can illuminate them individually with the laser pointer. Ooh. And if I use a flashlight instead, it still comes through. And I've got some pretty decent control. You've seen these kind of toys. Woo! Right? So it's got one purple LED in the bottom, and the light's just following these fibers. They're just they're just pieces of plastic. They're so thin that they become flexible. And when you come to the end, the light just comes out. And it sprays all over because the ends aren't very well characterized. They're just cut. All right? So you've seen this kind of stuff, I hope, just in various places. And we can send information with it. So here's a fiber running from a transmitting system, which I'll turn on. So now there's a red light emitting diode here. And that light emitting diode now is not just on steadily. It's actually winking. It's doing AM transmission, amplitude modulated transmission of sound, the sound from this radio. And over here is a receiver that watches is some radio. Is there an amplitude control? No. Can you hear the sound? So the sound is, it really is traveling in as light. Here, if I pull this out, can you see it's light on my finger? It's worked its way to this point, and obviously I've disconnected it from the receiver. If I put it back in the receiver, okay? So it's working its way up, meandering across the table. As long as that fiber isn't bent too far, and you don't do something that allows it to escape, the light, my finger won't do it. A question is whether that fiber is sophisticated enough to have a coating on it. If it doesn't, I may be able to mess it up with water. No, it's got a protective layer on it. Why the protective layer, I'll tell you in a sec. Well, let me show you how I can stop this thing. Turn off the toys. The simplest fibers, which are these probably are the simplest fiber. It's just a single piece of plastic or glass. And the reflective the surface from which the light reflects is the surface of that plastic or glass. If you go and touch it, I told you already, your fingerprints can allow light that was trying to do total internal reflection on your water glass, can allow it to reflect. Or on the side of an aquarium, same thing. Or water sprinkled on the side of the aquarium will suddenly allow light to get out because now the interface, that surface will be all at funny angles, and you won't get total internal reflection again, you'll just get refraction, something interesting. So with one of these fibers that is uncoated, or what's called unclad fiber, they're very vulnerable to junk on the outside. Water would be death, even just dirt. Like you can see, the dirt here was letting the light escape. Actually, I should put some water on the outside of that. Should I do that? No. I can, yeah. All right. So now there's water on that. If I can get the wet spots to get, oh, come on, get. So, yeah. It does. So the water now is changing. It should mess up the total internal reflection. But it's not. It's not. Is it doing it much? I'm still getting pretty much the same total internal reflection as well as getting wet, but it may be that water is too much like air, not enough like plastic. So water does slow down the speed of light. Maybe the speed of light in the plastic is significantly slower than water, so that the water isn't able to let the light escape, which sort of messes with one of the problems in the problem set. But the idea is certainly the dirt on that plastic was letting some of the light escape. And you were seeing light sort of released from its trapped environment as it encountered a dirt particle and was able to get out of the surface into the dirt and then go any which way. So unclad fibers are vulnerable to leakage. And that's okay if you want to just make a display of some sort. But if you want to convey information for 100 miles, you don't want any of that. So they put a cladding on the outside of the fiber, a layer that creates the reflective surface. That layer has to have an index of refraction that is lower than that of the core. So the light travels slowest in the core. It travels faster, but probably still less than in air, in the cladding. So you get it's a sandwich, but of course it's a cylindrical. So you have the slowest light travels slowest in the core of this fiber. This is a slice through a cylinder, right? The fiber is a long cylinder. You slice through it. Here's a picture of it. This is the cylinder in the middle, and this is the cylinder around the middle, the pipe in which the cylinder lives. And light reflects off the edge here between the core and the cladding. Is that okay? The cladding then protects the light traveling in the core. It never gets to the actual surface of the cladding. Light never gets to the surface of the cladding, and therefore there's no opportunity for it to leak. The reflection comes off in that. The total internal reflection occurs between the two layers. So any decent communications fiber has that arrangement, a core and a cladding. Evidently, this one probably has a core and a cladding. The fact that I can't make light escape from that plastic bothers me. I should be able to do it, but I wasn't able to do it. One other version of this demonstration that's kind of cute is water, you can send light in water. When you pour water, ultimately it breaks up into droplets. But before it breaks up into droplets, it travels for some distance as a stream, and you can get the light to travel in the stream. So that's what this demonstration does. Woo! When it's going to break up, there it's breaking up. But before that, it's traveling as a okay, so pipe for light. Again, total internal reflection, side. All right. Last details about fiber optics. The most obvious fiber optics, which are pretty much all the ones we have here, even once you put the cladding on, they're good for conveying information for modest distances, but not for super long distances. And the reason for that is because there are too many paths that light can take between its entry and exit. They can go at different angles, and light traveling at different angles travels different distances through the core, and consequently, a brief pulse of light, even the best light you can make, a pulse of a laser just blinking on and off, one wavelength, everything as good as possible. Because it can travel through different paths, it will, and the pulse that went in nice and short will come out slurped out in time, because the portions of the light that manage to go straight down the path will arrive first, and the ones that bounced a whole bunch of times will arrive later and later and later. So what started as a short pulse ends up as a longer pulse, and that limits how fast you can basically sort of send Morse code or any sort of digital communication. You can't, if when it's really echoey in a very echoey room, you can't talk as easily to one another because you keep hearing, hello, hello, hello. It's all slurped out in time. Is that okay? What do you do? Well, the first improvement on this kind of fiber, what's known as a multimode fiber, where the multimode means many paths down the fiber, was to introduce, instead of a sharp transition from the core to the cladding, they gradually changed the index of refraction from the core. So light travels slowest right on the core, but it gradually changes speed and speeds up as you go toward the cladding, and you get these curved paths for light. You've seen curved paths like that when you go on a really hot day, sunny day, and you're driving across the desert, and the road in front of you has funny shimmery things on it, and mirages and reflections of the sky. Where are those coming from? What's a mirage? That is light from the sky entering the air near the road, which is hotter and therefore less dense than the air everywhere else. That very hot air is less dense, and so the light coming from the sky is speeding up. It's trying to travel through it at a very shallow angle into a material in which it travels faster. Ooh, that's the recipe for total internal reflection. And you get total internal reflection. The light doesn't go into the asphalt, it bounces off that interface and comes up at you. So you see a reflection of the sky from, not from the road, but from those layers of air. Total internal reflection, same thing. And the transition isn't a sharp bounce, because it doesn't abruptly hit a surface. It hits this gradual speeding up, and it bends smoothly up at you and plays mirage. So that's light. This is upside. No, here it is. Here's light from the sky trying to hit the asphalt, and it bends up and it goes to your eyes. You see a mirage. All right? Don't try to drink it. The best thing you can do for optical communication. So the fibers that are really used for serious communication, they carry the internet, for example, they are single mode fibers. There is only one path through the fiber. And the fact that there's only one path through the fiber it makes use of the fact that light is a wave. It is not little particles traveling, like little bouncing billiard balls. Because it's a wave, if you make the core of the fiber on the order of the wavelength of the light itself, the light can't, its wave character becomes extremely important. You're making it work its way through something that's so small that it almost hates to be that confined, because it's too small for it. So the only path it has is straight down the pipe. It has, because it's a wave, it has an edge. It's brightest dead center, and it gets weaker and weaker as you go into the cladding, but it's basically confined to travel one path. And the result is that the light pulse you put in comes out. All the light goes together. No spreading, at least not because of path issues. And that's crucial for something like the internet, where you're trying to send gigabits per second or whatever, and you're going across the Atlantic underwater. You want to be able to send short pulses that are signaling information, and you don't want them spreading out into long pulses during their trip. Keep them together. So use single mode fibers. You're aware, I hope, that internet traffic and telephone communication all goes underwater and not by satellite. Early in the era of open season long distance telephone, there was an era when the long distance telephone was monopoly. AT&T controlled the long lines. If you want to make a long distance phone call, you used AT&T. In 83, 4, 5, that changed. It was broken up. The AT&T monopoly was broken, and people started being able to give you long-distance carrier service. And it was a free-for-all. Like, you're used to free-for-alls where something becomes possible and everybody hits you with spam saying, use my app, right? Some of those long-distance carriers use satellites. They bought time on satellites. The satellites are pretty high up. The ones they use are what are called geosynchronous satellites, which as the Earth rotates, the satellite orbits, they go together. So the satellite seems to hover over the same spot on Earth all the time. It's actually over the equator, too. It has to be. Okay, whatever. You know. But the satellite's about 20,000 miles up, and the time it takes for an electromagnetic wave, light, to go up to the satellite and come back down is longer than you guys want to wait. And it was too long for phone conversations. So when you got one of these connections that went by way of satellite, from here to satellite to down to Europe, for example, you would end up talking on top of each other all the time. So you pretty much had to play the old-fashioned radio game where you over and out, or or your turn to talk, my turn. They were very painful. Anyway, all the communications now goes by as fast routes as it possibly can. The fastest route is not satellite. Don't go up and back. You just go straight across, and so you have to go underwater cables. So lots of underwater cables. All right? They all use single mode fiber because you got to get pack as many bits as possible. Still one more source of trouble. If you're trying to send information on an electromagnetic wave, that electromagnetic wave necessarily has more than one frequency in. Because a pure wave, this is very pure, but it sends no information. To send information, I have to wink it on and off, or something like that. And once I do that, it's not a pure wave anymore. It has more frequencies in it than just its central perfect wave. It's spread out in frequencies. And the details of that is, interesting mathematics, but I'll stay away from it. The consequence of that is the high-speed communications going by way of fiber optics have a spread in frequencies. They've got a central frequency, but it's not pure. And the result is you're sending a spread of wave frequencies through glass. If you recall, the blue colors travel more slowly than the red colors. And that happens even in these laser-based single-mode fiber communications. The higher frequency end of that transmission travels a little faster than the low frequency end of that transmission. And that can cause trouble. It smears out the pulses. And so what they use, they typically operate these long-distance transmission fibers in a regime that is in the infrared to get away from, which gets them to the weakest part of the fiber's dispersion. What does that mean? That means that the fiber almost carries all the frequencies at the same speed in this range of frequencies. If you get high up in the blues, it really slows down the blue end relative to the red end. But you work down here at these low frequencies, and it's pretty much the same. It's called the dispersion minimum. They operate near the dispersion minimum at wavelengths that just the reds and blues go. The reddish end of the spectrum and the bluish end of the spectrum travel pretty much the same speed. And that's the story of fiber optic communication. Any questions? All right. So, end of that. Let me go on to a different topic then. The different topic is audio players. Oops. Audio players. And audio players is a collection. Over the years, I've done different things have evolved. This could just as easily be your cell phone, except it doesn't include the radio communication part of your cell phone. We've done radio to an extent. So the audio player story is a story of almost one thing. The next more sophisticated semiconductor device. I've talked about how diodes work. The next more sophisticated semiconductor device that dominates the world of gadgets you live with is called the transistor. And so this is partly the story of the transistor. How do I want to do this? Let me give you a quick introduction to the transistor itself. So the transistor makes everything about your cell phone possible. It allows it to handle information as basically be a computer and carry information as digital stuff. I've talked about how digital, the idea of representing information in digital form is take whatever information you like, whether it's pressure, the pressures involved in voice, in the sound of voice, or a textbook, or your latest text message. Text message, how do you represent text digitally? First off, you chop it into letters, which you're used to doing. So you got the letter E, for example, and you number all the letters from A to Z, and capitals differently than small, and all the punctuations. Just number them all, and now take a collection of symbols that can represent the number of the letter. So you want a collection of symbols that represents the 5th letter of the alphabet, E, and we'll make it a lowercase. And so it's a collection of symbols that'll do that. Well, the classic choice is 8 symbols that have only 2 possible values, which could be called up and down, left and right, 0 and 1. But they're symbols that are very simple. They have 2 values, and if you can distinguish between those 2 values, you got the symbol. And there are 8 of them, so you can represent a lot of different things with 8 of those very simple symbols. Like, you know, the first symbol might be this. This is binary, and I can go on at great length. For binary is just communication or data handling that involves symbols with only 2 choices. The fact that there are only 2 choices for symbols makes it pretty easy to tell them apart. If there were 100 different symbols, now you got to look carefully. It's tougher to handle that electronically, for example. So just 2 symbols. And so you represent every bit of information you ever wanted as collections of these binary bits, just ones and zeros, ups and downs, whatever you want to call them. So once you've got that, you can move information around as these numbers. Even if it's text, even if it's photograph, you just number all the spots. And you number their colors. And you just work with everything as numbers. It's like at MIT, where everything's numbered. Like buildings are numbered, classes are numbered. That's a little odd for me. Anyhow, how do you actually then move them around? And I mean, long distance, you move them, say, in fibers. I talked about that already. But if you want to move them locally and you want to do interesting things with them, you want to use devices that work very nicely with these 2-choice symbols. And one of the devices that works really nicely with those is what's called a MOSFET transistor. MOSFET stands for metal oxide semiconductor field effect transistor. You know, what does that all mean? It involves the field associated with electric charge, and it's using semiconductor. I mean, it's a complicated name for no particular value. But what we'll see that it does is that it allows electric current to flow or not flow depending on the presence or absence of charge on an insulated surface nearby called the gate. So the issue is going to be electric current can flow through this schematically, this structure here, which I have to explain, and I'll make some progress on it today. Current can flow from left to right or left, either direction, only when this surface that's nearby has, in this case, positive charge on it. In the absence of positive charge on that gate, no current will flow. In the presence of positive charge on that gate, current will flow. And how much positive charge do you need on the gate? Well, depending on the size of this little guy, it could be the charge on 10 protons. You know, the most amazingly dinky amount of charge you could imagine dealing with. So you put the tiniest amount of charge on this gate, and whoomp, this thing becomes electrically conducting. Take the charge off, whoomp, it becomes an insulator. The way it does that is this. It's made up of 3 regions that are chemically of semiconductor. Remember semiconductor? In a pure semiconductor, all the valence bands have electrons in them. And all of the conduction bands are empty, and the semiconductor is an insulator. That was the story of an insulator in general. Semiconductor is just a relatively weak insulator. So in pure semiconductors, this whole bottom area would be filled with electrons, therefore nobody can move. Remember, it's the full theater idea. And the balcony, the conduction band, has no electrons, so none of them can move either because there's nobody there. All right? But this is not made of pure semiconductor. It's made of 3 pieces of semiconductor. The 2 ends of this structure are made of N-type semiconductor, meaning that the atoms that have been put into it are not pure semiconductor atoms. They put in a couple of atoms that don't belong there normally and have more positive charge than the semiconductor itself, and therefore drag in more electrons than the semiconductor itself. And those electrons have to go somewhere, so they go into the conduction levels. So here on the edge, there are electrons in the conduction level of the semiconductor, where they wouldn't normally be. But they're there, both sides. The middle is chemically turned into a p-type semiconductor. It contains atoms that are short on electrons. On positive charges, therefore drag in fewer electrons and leave the valence band a little empty. There are a couple of empty holes when it was made. Okay? That's before this photograph was taken. So what you have before these 3 parts touch conceptually, when they're separated, the N-types at the ends both have some electrons in the conduction band. And the p-type, which you don't see it here, but when the p-type was originally made, it has a few missing electrons in the valence band. So individually, each of these pieces is able to conduct a little electricity because they've got some movable electric charges. Some of the electrons are not pinned down. They're empty spots to play with. When they touch, though, the electrons from the N-type material near the p-type material migrate into the p-type material and fill in all of its empty spots. And you end up with this depletion region, a region in which there are all the electrons, all the valence levels are filled, all the conduction levels are empty, and this cannot carry electricity. And that's a bad spot for electricity. No conduction. What can you do? If you put positive charge on that gate surface, which is separate, it's electrically insulated. That's the metal oxide semiconductor part. Metal, there's an oxide insulator here, and then the semiconductor. When you put the positive charge there, it attracts electrons. Electrons love positive charge, so they migrate into this region in the middle where there weren't any. And suddenly, this central region becomes electrically conducting. It's as if it's N-type material. It was made chemically as p-type material, short on electrons. And for electrical reasons, it becomes rich in electrons, N-type. And electricity can flow. So now, having talked this a lot, hopefully this makes some sense. I'll probably come back to it. But let me show you a MOSFET in action. And I've got one up here. And we can look down on it. I'll put it on the side camera. To document camera. We're now looking down on MOSFET. The MOSFET's right here. And right now, I'll turn on, I'll make it, so I'm going to go to more voltage. So there are now 4 volts across it, but no current is flowing. This tells you how much current is flowing? None. How much voltage is across it? 4 volts. No, it's in that original state, as though we're just constructed. That whole central region has no electrons in the conduction level, and all the valence levels are filled. How can it turn into a conductor? Put positive charge on its gate, the G electrode. Where am I going to get that positive charge from? From this wire. This is the positive wire. How am I going to put them on the gate? With my finger. You don't need much charge to turn it into a conductor. How about to turn it off? Take the charges off the gate. Put them on, take them off. Wax on, wax off. Okay? That thing is exquisitely sensitive to charge, and consequently you can control a big flow of electric current with the charge that can go through your finger. Well, with a little bit of care, you can build a device that amplifies. There's a MOSFET here too. That can amplify an audio signal from a very dinky signal to one that can power a speaker. So this device is putting charge on and off the gate of that MOSFET and turning it on and off and everything in between. And it's playing sound. You hear the sound? 1 second here. Right now, it doesn't seem like anything interesting, but I will become part of the circuit. So I'm going to take the charge coming from the player, and I am going to, come on, prove me wrong. Can you hear it? I'm now part of an electric circuit that's turning on. It's a little, we have better volume. More volume! Yeah, it's good enough. The point is the charge needed to make this work is so tiny that you can use terrible conductors or, anyway. This is the basis then of all kinds of electronic devices, and I'll do more of them on Monday. Meanwhile, you can come up here and become part of the circuit if you want to, too.